Hi everyone, I see that you should hear me. Today we will be talking about solutions to problem A to F from today's diff-free contest. I think that the first, three problems were mostly about implementation, so so we will show implementation to first three problems, because those were beginner problems, and to those three problems we'll just talk about ideas. Okay, so let's go to problem A. In problem A, problem A. In problem A, we are given three numbers, A, B, and C. And we want to divide those people into tenths. People of type 1. We have A people of type 1, B people of type 2, and C people of type 3. And the statement says that the people of type 1, they need to be alone in their tent, people of type B need to be with two other people in their tent, and people of type C don't care. They can be however they want. And also in one tent we can have up to 3 people. And now we want to say, is it possible to divide people into tents such that each person is happy? And if so, what is the minimal number of tents we have to use? Right? Okay. Yeah. Okay. So we see that we have to use 8 tents for the first type people, and then we only care about those two types of people. So now we see that when we divide people of type 2 into tents, we will divide them we'll just divide them into B divided by 3 tents, right? Because let's say if we have 5 people, those are people, then or 7 people, we'll create 1 tent for this people and 1 tent for this people. So we see that there will always be B modulo 3 people left. And so those B modulo 3 people, we need to match up with those C people of type 3. So basically the answer is no if B modulo 3 plus C is smaller than 2. Oh, and also if B is divisible by 3, then B modulo 3 is equal to 3, not to 0. That's important. And if B modulo 3 plus C is greater or equal 3, then our answer is A plus B plus C divided by 3, but we have to round it up. Right? Because, we have those B-type people, then C-type people, and we'll just do greedy, like this. And basically, this is the result of this greedy. B plus C divided by 3, but we have to take C. Okay. So, I can show you my code, because it was beginner problem. But I think everyone solved this. But still, there might be some beginners who want to see it. So, okay. Here I am saying what is B modulo 3. If B modulo 3 is equal to 0, then it's equal to 3, not to 0. That's what I said. Because, we want to know how many people will be left like here in this blue part. Right? So this is the blue part. And if B modulo 3 plus C is smaller than 3, then the answer is no. And in other case, we are counting A plus B plus C, but still of it. But as we know, in C++ we have floor in our dividing, so we know that ceil from x divided by y is equal to x plus y minus 1 divided by y. By y. So that's how you want to get ceil in C++. So to the more interesting tasks. Task B was also about getting the formula. So in this task we have two installations for launching fireworks, and first installation will launch fireworks in the 8th minute. 2a, it will be able to launch a firework every a minutes. Second installation will be able to launch fireworks every b minutes. So and we know that when launching a firework it will be visible m minutes. So the question that they give us, if we will be launching the fireworks like this, A, 2A, 3A, and B, 2B, 3B, and we'll be doing this up to infinity, right? We'll be doing this to the end of the world. What is the maximum number of fireworks that will be visible in some time in the world? I hope you understand, right? So I will show you maybe example test, because there might be someone who didn't understand. So in the first test case, A is equal to 6, B is equal to 7, and M is equal to 4. So that means that we'll launch fireworks from the first shooter at 16, 12, 18, 24, 30, 36, 42, 48, 54, and 60. I think that will be enough. And from this one, okay, so now let's look at this number 42. We know that it's the least common multiple of both, right? So I can prove that we know that this moment of time, such that the most fireworks will be visible in it, is somewhere around here, somewhere around LCM, right? So if we would look only at A, how many fireworks can be visible? How many fireworks shooted out of the first launcher can be visible at most at night, right? How many of the if we launch from A, how many fireworks will be visible, at most, right? Well, it will be M divided by A, right? Because we have some, of course, ceil, right? Because, well, we have some moment of time M, some part of time, and we can always assume that we launch the first firework here. I'm sorry, it's ceil, but +1. Yeah. And then we launch like the next, and we know that between each two fireworks the distance is A. So it will be M divisible by M. And well, it's the same for B. During M seconds there will be at most M plus B plus 1. There will be at most M divided by B plus 1. This is the number of fireworks that are seen during one moment. The most fireworks that are seen during one moment. So, well, if we'll start this thing from our LCM, then we know that we can just sum these numbers, right? Because, well, we can treat them independently. Because in this number, both of them start or something. So we can treat it as 0. So this is our answer. M divided by A plus 1 plus m divided by b plus 1. Okay. So to the next problem, because those are not really hard or interesting. Okay. In problem C, we have some problem C. In problem C, we have some 0, 1 string. So let me write example test. Okay, I can explain how I get the m divided by a plus 1 and m divided by b. So first what I am saying, will tell it once again. So first what I am saying, we can treat both of them independently and then just sum it up. Because we see that if we start in LCM, then we can just treat both of them independently, right? So now the thing that we want to say, when we are starting some firework launcher A, such that it fires the fireworks every 8 seconds, how many fireworks will be visible in one moment, right? So we know that the first firework will be the first firework will be active up to moment a plus m, right? So we know that we want to find the number k of fireworks, the biggest such k, such that a times k, so the k firework, is still smaller than a plus m, right? I hope you understand it. Because that would mean that if we will find biggest such k, that would mean that at most k fireworks can be visible at night. And well, if it's satisfied, then we know that also k fireworks can be seen. So if at most k can be seen and k can be seen, then well, it's like the biggest possible. So by doing some things, we have a times k minus 1 must be smaller than... let's say that the first firework is in the... Oh no, that's okay. That was okay. So well, we want to find the biggest such k, such that k minus 1 is smaller than n divided by a, right? So we know that, well, we know that it means that k minus 1 is equal to m divided by a and floor of it. So k is equal to m divided by a, floor of it plus 1. And that's exactly what I said before. I hope you understand now. Yeah, does everybody understand this? Yeah, I think this should be like good explanation. Okay, so now to problem C. Okay, problem C. In problem C we have some 0, 1 array. So let's, I will, oh no. I will, let's say take this array. Yeah. And we want to divide it in some point, right? We have n plus 1 possible divides. Oh, let me wait. Draw it. 0, 1, 0, 1, 1, 1. And we want to divide it in some point. We have n plus 1 possible dividing point, because we can divide here, 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 and here. Oh, maybe like this. So we want to divide it in some point. And we want to divide it in some point such that left to this point, at least we want left to this point the number of zeros to be bigger than length divided by 2, and we want right to this point number of ones be greater or equal than length. Like, let's say that we have b numbers here and a numbers here. Then we want number of zeros in the left to be greater than a divided by 2, and number of ones to the right be greater than b divided by 2. Great. So now we want to such the dividing point such that both of those such that both of those things are true, and such that it's closest to the middle. So how to do it? Well, it's implementation problem 2. You would like to implement prefix sums over number of zeros and suffix sums over number of ones. And then when we are checking the some division point, we know how many ones we have to the right and how many zeros we have to the left. And we need to check both of those conditions, see if they are true, and see how close we are to the middle. So now I will show the implementation. Or maybe no. Or maybe someone wants it, I don't know. So I'm keeping how many zeros to the left and how many ones to the right. Right? And I am saying that at the start all the ones are to the right. Right? In the string. So, and I'm keeping the distance from the middle. I'm checking if this is true, right? This is what I wrote here. But this is our A, and this is our B. This is our B, and this is our A. As I said before, CIL from A divided by 2 is equal to A plus 1 divided by 2, right? In C++. And then what I'm doing here, I'm recalculating the distance from the middle. Basically, those are just some stupid ifs to deal with the idea that we can have two different, because, well, we are not taking the floor in this task. We are, like, in this task, and 3 divided by 2 is not equal to 2. 3 divided by 2 is equal to 1.5. So we know that the two closest things to the middle are 1 and 2, not only one as we would say here, right? And then if I'm now moving my division point to the right, and well, if now I am having some 0 left to me, then I am making it greater, and if it was equal to 1, this thing, then well, now this one is left to the division point, so I need to make it smaller by 1. Okay, I hope everyone understands. Now to those 3 more interesting problems. So problem D. So in problem D, we are given. Someone want to explain it again? Basically, the idea is to just brute force all the possible division points, because we have only n+1 of them. And for each point we are checking we are checking if the conditions are true, right? If the conditions are satisfied, and to check the number of ones right to it and the numbers of zeros left to it, we will use prefix and suffix sums, right? I hope now you understand it. The idea is just brute forcing. Okay, so let's go to problem D. In this problem we have some queue of people and each person have two values, AI and BI. So let me draw the example test. So okay, this is example test. Yes, this video is this video will be as usual available after the stream, so if you also I will be happy to answer your questions during stream, because that's why this stream is happening. But if you don't understand something after like second or third time that I say it, then I think you should replay the video and maybe something will come to you. So each person in the queue have like two values, AI and BI. And we are also given some number m. In this example, I think it was like 2. Yes? And that means that we want to be in one of those first two positions in our queue. And well, in the start we are like at the end of queue. And we are also we also know that when we want to go after some person in this queue, before this person, then we need to pay this person AI, and every person between us we need to pay BI plus sum of BI, BJ over all J greater, right? So we are paying BI to all the people between us. So for example, in this example test we would like to move straight to the wait, I don't know really how, but in this example, let's say if we would like to move straight to the if we would like to move straight to being before the second person, then we would have to pay 3, because 3 is AI of the second person, and then 8 and 5, because those are people between me and this guy. So we would then pay 16. But I think we can do 14 in the example test, so it's not good. Yeah. So I think there's, as I see now, there are probably some easier solutions than mine, but mine is also good. And like it's more it's like something you can use in many tasks. So we'll do dynamic programming, and the P from I will mean the minimal cost. Maybe I will write it with my keyboard. Minimal cost to move. Oh, and the tasks ask us what is the minimal cost to move to one of the first m positions. So in the first example, we would like to move to one of the first 2 positions, or after 2 positions, I don't know. Minimal cost to move to first m positions, starting after position I. So basically our answer will be the P from n plus 1. Or before position I. I'm sorry, before position I. Position I. So, well, now we see that dp from I, we are iterating in our, it's minimum. We are iterating over all j smaller than I, right? J will be the point that we'll jump to, and it will be dp from j plus cost of the jump. And what is the cost of the jump? It's ai, aj plus sum of all k such that they are between me and j of b k. Okay, this would basically allow us to do n to the power of 3, but we want to make it up to n. So first, how to get it to n to the power of 2? Well, we can do prefix sums to do this. So now, if we do prefix sums, I hope everyone who watches it now know prefix sums. If no, then, well, it's good to know prefix sums. It will be dp from j plus aj plus sum from I minus 1 minus sum of j. Right? And sum from I means sum from I don't know, j equal to 1 to I to bj. Right? Those are just prefix sums. So now we have n squared. Because, well, we would need to iterate over all j's. But we see that this thing only depends on our I, right? So for all j's, this thing is the same. So we can kinda cancel it. And, well, we can then just find minimum over all those three values, right? So we have dp from I is equal to sum of I minus 1 plus minimum so basically when we calculate some dp, when we calculate some dp, we basically want to we are keeping some variable that will say us what is the smallest possible value of this that we already encountered. And when we are calculating some dp, then basically we know this value here, so we can easily calculate it. I hope everyone understands. Oh, the minimum from j smaller to I is basically like a for loop. For loop that says, look at all the j's that satisfy this condition here and take the minimum of the values here from all of those j's. Yes, I will show my code. Someone said that we don't need to use the dp. Yeah, I see it now too, but I think the dp is more educative than some greedy or something like this. Because basically, I think for each problem, we basically, if someone wants to know this other solution, we see that for each person in the queue, we either have to add its bi to the answer or ai, and we can take like minimum of those two values. So it's easier. You are right, it's much easier, but I want to show this solution because, well, many problems are solvable like this. So basically what I'm doing, I'm calculating prefix sums here, and I'm calculating my dp. If I is smaller than m, then, well, minimal cost to move to first m positions is 0, because I am already here. And otherwise, it's this minimum of those, it's this minimum plus si minus 1, right? Because that's what I wrote here. And what I'm doing now is, well, I have found new dp, so it's good to say to my minimum variable that, well, you have new thing that you need to consider, right? And, well, this is thing here. Okay. So I hope everyone understands. So to problem E. In problem E we have some weird binary search on unsorted permutation, and we want to make sure that this binary search returns number x, right? And we want to make it sure by swapping two pairs of indexes in this permutation. Okay. So, problem E. I think this was the first problem in this round that required some thinking or something harder. This could be normal, I think, div 2c. This problem. This could be normal div 2c. So, I can send it to chat. Basically, this is what dp from I means. So problem E. Now. So, yeah, we want to swap at most two pairs of indices such that this weird procedure that ends up with PL equal to X. So there's basically only one observation in this task. The observation is, or maybe we have, let's say that we go through some m's here, right? Let's say that first our m here is equal to 5, then something happens and it's equal to 7, then something happened. So let's see at the set of possible m's. No, not possible m's, but m's that we'll go through in this binary search. Because, well, we only care about value of PL and about those values that we have here, the values that we compare with x. So let's say that they are equal to 5, 4, then 3, then 1. No. 5, 7, 9, and 8. So basically, I say something like this. If let's say that the I such that pay I is equal to x, given in our task, let's say that this is pose, right? Let's say that we call pose the position such that pay I is equal to x, right? So I say that if we don't go through our position, like we don't compare with our position doing binary search, then we can just swap our position with the ending L. And we will always go to L, like in this procedure, because we haven't changed anything. And well, in the end, it will be equal to PL, right? Okay. So now the most beautiful observation in this problem. We will never we'll never compare with position 1. Oh, you don't see my board? No, you see my board. Okay. The most beautiful observation is that we never compare with position 1. Why? Because the shortest interval that we have starting on position 1 is interval 1, 3. And we know that the middle point of interval 1, 3 is 4. And is 2. Anytime that we are making it bigger by 1 to the right, well, this one gets bigger too. So we know that we never compare with the position 1. So what we could do is we could, well, just first swap our number with position 1, our position with position 1, and then we could just implement this procedure, find the L, and swap with position L. I will show you my code. So basically I'm finding this position such that pi is equal to x. I'm swapping it with position 1, and then I just copied bin search from the statement of task. And then what I'm doing, I'm swapping the position 1, because right now I know that p1 is equal to x. And I am swapping it with position L. And then I am just counting the operations. Yes, I will explain when we never round on position 1 once again. All intervals such that they contain position 1 are 1, 2, 1, 3, 1, 4, and up to 1 and plus 1. Right? You agree with me. And let's look at the middles of those intervals. This interval is the ending interval, so we won't compare with it. We will never compare with it. This interval has the middle 2, right? Because 1 plus 3 is 4, divided by 2 is 2. This interval has middle 2. This interval has middle 3. So do you see that the smallest possible middle is 2? And with making our right endpoint bigger, the middle gets bigger too. So we will never land on position 1. Do you see it? Okay. Yeah, it's pretty beautiful observation. Right, so explaining it once again. We want to swap our position with such position that we will never compare with in bin search. Cause, well, if we would swap with some position that we used to compare, then we could destroy something. But we know that so AM is always smaller than X. I don't understand. It's not always smaller than X. We want to swap with some position such that this position is not compared with, right? So we want to swap with some position such that this position is never compared with. Because if we would swap our position with some position such that it's compared with, well, then we would fuck up. We would destroy the thing. It would just be destroyed. And okay. And yeah, I'm sorry. I'm really sorry. And so and basically the thing is that we want to swap our position with PL, but we also want to make sure that we doesn't compare with position before, right? So to do this, we will swap our position with P1, because as I shown, we don't compare with P1 ever. So let's go to the next problem. The next problem was about implementing segment tree. So this will be the last problem that we'll talk about from today. I'm really sorry about my language. So problem F. Yeah. So in this problem we have some mushrooms and their values. So and we know that when we pick some subset of mushrooms, let's say first mushroom and second mushroom, then our score will be the sum of all values times the number of values. Right? So here it would be 17 times 2. But we also know that when we take k values, we have first k minus 1. So let's say that if we take first two values, then we can't take the index 3. Index 3 can't be one of those values. If we take first if we take some free values, then index 3 and 2 can't be part of those values. Right? So we know that if we take k values, one of them can't be p1, p2, p3, up to pk minus 1. Right? Those are like, I don't know, we can't take them to our subset. So now what we want to find? We want to find the greatest score that we can get. So we will iterate over the number of values that we take, right? And then, well, what we would like to find, we would like to find the k biggest values, such that none of those values is one of these. None of those indexes. So we know that none of the... So we want to find the... Oh, I'm sorry, it's not sometimes. Yeah, it's minimum. Yeah, I am stupid. It's minimum times this, so here it would be 8 times 2. Okay, that's easier, yeah. So we would like to find the k biggest value, such that we have some blockaded values, blockaded indexes. And from unblockaded indexes, I would like to find the k biggest value. That's basically our task. So, well, this is standard segment tree task. We are doing segment tree over values, right? So we are keeping like 1 in the index 14, 1 in index 8, and 1 in index 9. And now we would like to find on our segment tree the longest such suffix, this shortest such suffix, such that the sum on this suffix is greater than k. So this is well just going recursively down in the segment tree. And now when we say that, well, now we want to find the longest we want to find the cave plus 1 value, we also need to blockade p cave, right? So we are subtracting 1 on value from pk. So basically we would like to find the cave value, and we would like to the cave value from unblockaded blocks. So when we want to find the cave value with updates, this is just segment tree over values. In every value we keep how many numbers have this value, right? How many unblockaded numbers have this value? And then we want to find the longest such shortest such suffix of values, such that the number of values on this suffix is at least k. Because, well, we know that, let's say that the longest such suffix is 5, and on those suffix we have 4 values. We know that if we would like to take the value 6 as our cave value, then it wouldn't be, we couldn't take it, because there are less than cave values here. So, let me show it. Basically, I am converting the values. That is really important because the values are up to 10 to the power of 9. I'm converting them here, and then I am just having segment tree for sum. And here is going downwards on segment tree. If I can go right, then I am going right. If I can't, then I am going left. And basically what I'm doing, I'm finding the cave value from unblocked values, right? Using this function. If there isn't cave active values, then well, I'm breaking because there are too many blocked values. Otherwise, I'm updating my maximum and I'm saying, I'm sorry, but the value pi is now blocked. So, sorry for saying this so quick. I hope that everyone understands. This stream will be saved, so it's good to see. I will also send you my code, because I think if someone doesn't know this going down on segment tree or finding the cave greatest number on interval but with updates, then I think you should look up to it, to my code, because I think I didn't wrote it really bad. I wrote it pretty good. So thank you for hearing this and see you next time. Does anyone have any questions? Yagan says, how to do problem D? I assume my DP from I has minimum amount to reach if position from n+1 position. It's not bad actually if you say it like this. You just need, I won't, you can replay the video and see, but I think your solution would look really closely to mine. The hint is to speed it up from n to the power of 3 to n to the power of 2, you need to use prefix sums, and to speed it up from n to the power of 2 to n, you need to group the formulas. So you need to group the formulas such that everything that is like bonded to j is here, and everything that is bonded to I is here. If I use zero-based index in binary search, when I should use high and when high? Well, I am always writing binary search like this. Let me show you my code to binary search. So, if you ask me how to write binary search, I am always writing binary search like this. You have two possible binary searches. One of the binary searches will say something like this. If the condition is true or not true, then if the condition is not true, then for all the smaller numbers it will also be not true. Otherwise, if it's true for me, then for all the bigger numbers it will be also true. Right? And then you need to, well, then you have something like this. But the other case is when the condition is true, then it's also true for all the smaller numbers. But if it's not true, then for all the bigger numbers it's also not true. Then you also need to get +1 here. So those are two possible binary searches. If you do 0, it will be the same with 0. You just need to do like this. So thank you for stream and see you next time. I hope you like it. Stay tuned for more, because I think this channel is growing pretty fast. Also, I should send... Oh. I should send Discord link, I think. So let me share my Discord, the Discord of this channel with you. I think this channel is growing pretty good, so you should probably stay tuned for more, because there are many good things for beginners and even intermediate people. So stay tuned and bye. I hope you like it and you taken something out of it.